Hi everyone, this is your video for chapter 3. We're going to go over some math basics and introduce to you the topics of error analysis. Let's get started. The opening to this chapter starts with this paragraph. Let's suppose we measure the density of a mineral by finding its mass, which happens to be 4.635 plus or minus 0.002 grams, and its volume 1.13 plus or minus 0.05 mils. What is the uncertainty in the computed density, and how many sig figs should be used? This chapter is going to help you answer these type of questions because it's not as simple as just adding those uncertainties. There's a bit more that goes into it, and we're going to learn all about the real rule of significant figures when it deals with error analysis. Every measurement that you do has an error associated with it. So we have to express those errors correctly with the correct number of sig figs, and that's what we're going to learn. What are the purpose of sig figs? Well, it gives us the minimum number of digits needed to write a given value without the loss of accuracy. Remember, the whole point here is that we're doing a bunch of chemical measurements, and you don't want to lose any accuracy when you're trying to compute the numbers from your data. There's 4 rules that you should know already. The first one is any number that isn't 0 is significant. The second one is the sandwich rule. That's any 0 that's between 2 non-zero digits is significant. The next one is zeros before the first non-zero digit are not significant. They're just there to hold the place of that first digit. And then the zeros after rule, which is zeros after the last non-zero digit are significant only if there's a dot. Let's do some problems to make sure we remember these. Let's try these. How many sig figs are there in each number below? The first one says 1.9030. Well, I know that the last 0 is going to count because I see a decimal place. And of course, the 0 between the 2 numbers is sandwiched in, so that one always counts. So there's a total of 5 significant digits in that first number. What about number 2? Here we have zeros before the first non-zero digit. Those zeros do not count ever because they're just there to hold the place for that first non-zero digit, the 3. What about the 0 after? The 0 after counts because there's that decimal place in that number. So there's a total of 4 sig figs in that number. What about the third one? There's going to be 3 sig figs in that one because, again, there is a decimal place. And that 0 counts because I see that decimal place in that number. What about the last one? It's 10,000. Do you see a decimal place? No, you do not. So that means that there's only 1 sig fig. All the zeros after that last non-zero digit are insignificant if you do not see a decimal place. Those zeros are just there to hold the 10,000 place for that 1. So again, there's only 1 sig fig in that number. I hope this brings back good memories because we're going to do these and much harder ones when we deal with error analysis. All right, let's move on. What about sig figs in arithmetic? Well, you should remember that when you're adding and subtracting, the number of sig figs is determined by the least number of digits you have in your numbers. Because remember, you can't be more accurate than your least certain data point. What about multiplying and dividing? Well, that's the easy one. That's just the least number of sig figs in either of the numbers. Maybe you guys haven't done logs or anti-logs, but here is the rule for them. It's quite simple. The sig figs in the number equals the sig figs in the mantissa. Now, the mantissa is just a fractional part of a number. So for example, that 2.530, the mantissa is the 0.530 part. The rule states if you're doing logs, so the log of 339, how many sig figs does that number have? 339. It's got 3 numbers, 3 sig figs. So that means that your answer for that log should have 3 digits in the mantissa part of the answer. So that's why it's 0.530. I know if I was to ask you how many sig figs does that answer have total, well, yeah, it's 4 sig figs, but there's 3 digits after that decimal place because there's 3 sig figs in the original number. What about the next one, which is log of 3.39 times 10 to the negative 5? It's the same rule. There's 3 sig figs in the number 3.39, so that means that there needs to be 3 sig figs in the mantissa part of your answer. So that's why it's 0.470. What about the anti-log? It's actually the same rule, but opposite. An anti-log of negative 3.42, that's your number, but how many sig figs are in the mantissa part of that number? 0.42. So there's 2 sig figs in that part. So that means that your answer is going to have 2 sig figs total. It's negative 3.42 would be equal to 3.8 times 10 to the negative 4. I hope that doesn't confuse you too much. I need you to practice these because we will use them this semester. Let's move on. Let's do some of these to make sure we understand the rules. How would you express each answer with the correct number of digits? The first one is an addition problem. So if you wrote it out like a 3-year-old, because that's what I do, you would see that it should be only 3.71 because the number that has the least number of digits is the 2.69. There's only 2 decimal places there, so that means that your answer should only have 2 decimal places. What about the second one? It's multiplying and dividing, so we see that the first number has 3 sig figs, the second number has 2. So that means that your answer is going to have 2. So the answer would be 40 dot. You have to put the decimal place because if not, that 0 does not count after that 4. So it's 40 decimal. What about the third one? This is just a division problem. So again, you take the least number of sig figs. The numerator has 3 sig figs and the denominator has 4. So that means that your answer will only have 3 sig figs. So it should be 2.85 times 10 to the negative 6. So here are the new ones. What about the log of 4.218 times 10 to the 12th? Well, you see that the number has 4 sig figs in total. So that means that you're going to have 4 numbers in your mantissa of your answer, in the fractional part of your answer. If you take the log of that number, you should have gotten 12.6251. And you notice that there's 4 digits in the mantissa because, again, you have 4 sig figs in that number. What about the antilog of negative 3.22? The antilog, you take how many digits you have in the mantissa, which is 2. There's 2 sig figs, it's 0.22, so there's 2 sig figs. So that means that your answer should only have 2 sig figs total. And if you take the antilog of negative 3.22, you should get 6.0 times 10 to the negative 4th. What about the last one, 2.384 base 10? That would be the same rule as your antilog. You have a total of 3 digits after the decimal place, so 3 digits in the mantissa part, so that means that your answer is only going to have 3 sig figs. The answer should be 242. Okay, let's move on. Section 3.3 in your book talks about the types of error in an analysis. Every measurement has some type of uncertainty. You cannot completely eliminate your error in any process that you do. That error is called experimental error. So whenever you do an experiment and you publish a conclusion, those conclusions must be expressed with a high or low degree of confidence, but never with complete certainty. Basically what that means is the true value of a measurement is never really known. You can get as close as possible to the true value, but you really can't get to the true value itself. The magnitude of that error can be evaluated, so you know how confident your data point really is. And we're going to learn about all that and how to compute all those errors later on. But these magnitudes can help to define the limits at a given level of probability. So for example, what I mean by that is without this reliability, the measurement is useless. You can't just say that you've measured such and such and it's 29.4. Well, it's 29.4 plus or minus what? What is your error associated? What is your uncertainty associated with that measurement? Everything has an uncertainty. And as the last bullet says, there's really no simple way to assess reliability. There's all kinds of different ways, but they're all pretty tedious. You can either use standard, any glassware that you use in your experiment has to be calibrated, so you can use calibrating glassware. And there's, of course, statistics, which we're going to talk about in the upcoming videos. Like I said, there's 2 types of experimental error. There's either systematic or random. Let's talk about systematic first, which also is called determinate error. Random error is also called indeterminate error. Systematic error can be discovered and corrected. For example, suppose you were weighing out some water in a burette that was uncalibrated. That's a systematic error if you can discover it and correct it. The manufacturer's tolerance for that burette that you're using is plus or minus 0.05 mils. So for example, when you think you've delivered 29.43 mils, the real volume could be 29.4 mils and still be within tolerance. One way to correct for an error of that type is by constructing an experimental calibration curve like the one I'm showing you right here. So what you would do is you would go ahead and deliver the water from the burette into a flask and weigh it. convert that mass of water into volume and do that for a couple of points, and the graph should tell you to apply the correction factor that you need. For this instance, it tells us to apply a correction factor of 0.03 mils to the measured value of 29.43 milliliters that we originally got, to reach the correct value of 29.4. Realize that systematic error can be positive or it could be negative. The error is repeatable, so if you don't notice it, that error is going to always be there. But if you're, like the book says, if you're clever, you can detect it and correct it. Let's move on. There are other ways to detect systematic error besides the calibration curve that I talked about previously. You can analyze samples of known composition. For example, use a standard reference material, something that you would purchase from NIST, National Institute of Standards and Technology. So you can analyze samples that have a high value of certainty against what you think you're supposed to be getting. Another way to detect it is you can analyze blank samples containing no analyte. So if you observe a result that actually gives you a data point, then you know that your method has to subtract that amount, because your blank is giving you a response. So that response has to be subtracted from your actual data. You can also use different analytical methods to measure the same quantity. If the results don't agree, then there's some sort of error in one or more of those methods. Finally, you can use a round-robin experiment, which basically means to analyze identical samples in different laboratories by different people using the same or different methods. The results should be the same anywhere you do the experiment if you follow the experiment exactly the same way that you did it. The other type of error is called random error or indeterminate error. And this arises from limitations on our ability to make physical measurements and on natural fluctuations in the quantity being measured. As I've written here, it has an equal chance of being positive or negative. It's always present and you can't correct it. It's kind of not fair, but it is there, so you have to realize that it is. It is small enough that you can't detect it individually, but any accumulation of it would cause your data to fluctuate. Some examples of that would be with someone reading a scale. I mean, different people reading the scale report a range of values representing their interpolation between the markings. One person reading an instrument several times might report several different readings, so that's random. You can't really correct that. Another indeterminate error comes from random electrical noise in an instrument. You have positive and negative fluctuations occur with approximately equal frequency, and you can't really eliminate that. And yet another source would probably be variation in the quantity that's being measured. So your book gives you an example. If you were to measure the pH of blood in your body, you might get different answers for blood from different parts of the body. And the pH at a given location might vary with time. So these are errors that are always there, but you can't correct them. You just have to know and accept it. All right, let's move on. The last thing I want to talk about in this video is precision and accuracy. Precision is the measure of reproducibility of a result. Accuracy is how close you are to the true value. A measurement can be reproducible, but it can be wrong. And your book gives you the example. If you made a mistake preparing a solution for a titration, the solution would not have the desired concentration, but you might do that same mistake over and over and over again, and your answer is always the same, but it's always wrong. So that's being precise but not very accurate. On the other hand, it's possible to make poorly reproducible measurements clustered around the correct value. Of course, the ideal is to be precise and accurate at the same time. Here I've given you 4 people that are shooting at targets. What would you say the first one, Cheryl, is? Well, she's neither near the target and none of her shots are even close to each other. So I would say that she is neither precise nor accurate. What about Cynthia? Well, Cynthia is actually close to the target, but she's not very precise. So I would say that she's precise, but not accurate. Carmen, now she's the one who's got it going on because she is both precise and accurate. You want her as your shooting partner. What about Chastity? Chastity, unfortunately, is very precise, but not accurate at all. She's not even close to the bullseye. So those are the differences between precision and accuracy. Well, that does it for this video. I will see you next time.